Hi everyone, today we're presenting on electric flux and Gauss's law, focusing on how the electric field behaves near an infinite plane of charge. This is group effort by me, Thenupa Fardin Seyam. I'll be starting things off with the basic concepts you need to understand what comes next. Here's what we'll cover today. Firstly, I'll explain the electric flux and the idea behind Gauss's law. Then we will show you how to apply Gauss's law to an infinite plane using a special shape called Gaussian surface. Finally, Sam will wrap things up with a real-world example and a summary graph. Electric flux and Gauss's law might sound complex, but we're keeping things very simple today. These concepts are used all the time in physics engineering, especially when working with electric fields and components like capacitors. We'll explain what the formulas mean and why they work using visuals and real-life comparisons. Let's start with electric flux. Flux measures how much electric field passes through a surface. Think of it like wind blowing through a window. The more direct and stronger the wind is, the higher the flux. If the wind passes past the window, um, if it slides past the window, very little air gets through. That's like zero flux. The formula for this is V equals EA cos theta. E is the electric field strength, A is the area, theta is the angle between the field and the surface. Maximum flux happens when the field goes straight through the surface. No flux happens when the field is parallel to the surface. Now let's connect this to Gauss's law. Gauss's law says that the flux through a closed surface depends on the charge inside. Imagine surrounding a charge with a balloon. The field lines that come out are related to the charge inside. The equation for this is that's gonna be it's here. Yep. So the equation for this here is phi is the phi is equal to q inside divided by epsilon naught. Here phi is the total electric flux. It tells us how much electric field passes through the surface. Q inside is the total charge enclosed by that surface. Epsilon naught is just a constant. It's called the permittivity of free space.
So now we'll be going through the process of choosing the right Gaussian surface for an infinite plane. For an infinite plane with uniform charge distribution, we use what's called a Gaussian pillbox, a cylindrical shape. This pillbox has two flat circular caps and a curved side. In the image, the two flat circular caps are labeled as N1 and N3, and the curved side is labeled as N2. The brilliance of this choice is that the electric field from an infinite plane is always perpendicular to the plane's surface, which means the field pierces the flat caps perpendicularly, giving us the maximum flux through the surfaces, and the field runs parallel to the curved side, means zero flux through that path. This careful selection of our Gaussian surface is what will make the math work out so easy. We'll be seeing the summary of electric field on the pillbox, and in the picture we can see that there's this infinite plane, which is the red area, which is the positive charge. That's why we can see the electric field is going out of the pillbox, and that's parallel. It will be parallel here. That's parallel to the fill caps, and we have done the calculations, and we can see the total flux through the flat plane is 2EA, and the curved side has zero flux because the electric fields are perpendicular to the curved side. That means the theta is equals to 0 and cos theta will be 0. So basically the total flux of the curved side will be 0. So this is basically the summary of the electric field on the pillbox. We'll be calculating the total flux through the pillbox, and to calculate total flux through the pillbox we'll be using this particular formula. So previously we have mentioned that we have three surfaces. which is two of them are two flat caps which are at the top and at the bottom of a pillbox, and the other one is the curved surface. So if we want to calculate the electric flux through the flat surfaces, we have to consider theta is equals to 0, because we know the electric field is perfectly perpendicular to the caps. So we have to consider theta is equals to 0 and cos theta will be 1. So if we put cos theta into that formula, we'll get electric flux is equals to simply the multiply of electric fields and the area. So then if we want to get the total flux of both of the flat caps, we have to add those and we'll get 2EA. Also, if we think about the curved surface, we know that the electric fields are parallel to the curved surface. That means the theta will be 90 degree and cos theta will be 0. So basically if we put cos theta into the formula, we'll get the total flux which is equals to 0. So we won't be considering that. Also, now we'll be using Gauss's law, which is Q by epsilon naught, and we'll be using the charge density formula, which is sigma is equals to Q by A. So if we now we'll substitute everything basically to get our final result, and our final result will be 2EA is equals to sigma A by epsilon naught. So this is our final result, which shows the electric field is constant everywhere, determined by the charge density and only some fundamental constants.
Look at how electric field changes with distance, but this time for an infinite plane of charge. With a point charge like a single electron or proton, the electric field gets weaker as you move further away. The strength of because of the field spreads out, but with an infinite plane, does a very surprising thing. It doesn't change, no matter how far you go. It doesn't get weaker at all. This happens because the plane is so large. As we move closer or further away, the field stays constant. On the graph, you can see a flat horizontal line. That means the electric field is the same at all distance. It doesn't increase or decrease. That's a key difference between an infinite change, that it stays constant and it doesn't increase or decrease with distance like a point charge. A great example for it would be a large capacitor plates. So you might ask the question, do we see this in real life? A great example is inside a capacitor, especially a parallel plate capacitor. If the plates are big and flat, the electric field between them acts like it's coming from an infinite plane. This field, the plate stays constant and uniform, just like as we saw before. That's why Gauss's law is so helpful while designing electronic devices. It helps us understanding of how we can control the electric fields in things like capacitors. Thank you for listening and joining in. Hopefully, this helps you to have a greater understanding of Gauss's law and electric fields. We would like to thank the OpenStax Physics textbook that we help to get citation and references from. Thank you. Have a good day.